Ever been so bored that you started running in circles and calculated your centripetal acceleration? Probably not. But welcome to our informational video on circular motion. Case study, the discus throw.
Our project focuses on the physics of a discus as it is swung around and then released by our good friend Gerd Kanter, an Olympic discus thrower from Estonia.
For your career in circles, you are going to have to get used to the following. Unless you're looking at a clock, things tend to accelerate as they go in circles. Whatever speed the object flies off at when it is released, multiplied by its distance from the center, equals the centripetal acceleration.
The force that maintains motion in a circle is calculated by its mass times tangential or fly-off velocity divided by the distance from the circle's center.
To figure out how fast the object flies off when released, multiply the distance from the circle's center by the velocity it is spinning around at.
To find the spinning angular velocity, divide the distance in radians by how long it takes. For instance, one full revolution's distance consists of 2 pi radians. In 1 second, the angular velocity would be 2 pi radians per second.
The radius of the circle is approximately half of our good friend Gerd's wingspan. A person's wingspan is the same measurement as a person's height. Gerd is 6 feet 5 inches tall. Converting this to meters, he is 1.9558 meters tall. Divide this by 2 and we have a radius of 0.9779 meters.
Observing his wind-up, the discus makes approximately 2 rotations. Each circle consists of 2 pi radians, so the discus travels a distance of 4 pi radians. This is the angular distance.
Still observing the video, staring down the seconds bar, this occurs over a period of 1.5 seconds. Remember our omega equation before for angular velocity? Divide the distance, 4 pi, by the time, 1.5 seconds. In the end, we get an angular velocity of 8.378 radians per second.
Using the above discovered angular velocity, we can find the tangential velocity. Simply multiply the radius in the angular velocity. The discus flies off at a speed of 8.193 meters per second.
Knowing the tangential velocity, we can solve for centripetal acceleration. The tangential velocity squared divided by the radius is the centripetal acceleration. In this case, 68.642 meters per second squared.
Lastly, we already have had the information to solve for the centripetal force. We chose to calculate using mass times tangential velocity squared divided by the radius. The force comes out to be 137.284 newtons.
So the next time you're watching the Olympics and our good friend Gerd, remember to calculate his centripetal motion.